So okay, let me continue where we left off last time. So we are saying like okay, we are talking about like KL divergence like last time near the end, and KL divergence, if you remember, like if we have two distribution, like it can be either discrete random variable or continuous random variable. So if it's discrete, then of course px and qx here will be PMF, and if it's continuous, then it will be like PDF. So we can use the KL divergence to estimate the distance between these two distributions. And so we have mentioned several examples. Like the last example, like we talk about near the end, is like we can use that like for text search, for example, like or like document comparison. So for example, like you have two documents here, and we say okay, we can create a bag of words kind of distribution. So for example, like this have a document one is an expensive bag, and the bag is expensive. Then we can just like kind of enumerate like all the words distribution, and then like we find okay the probability for it, for example, is like 1/10 and so on. And similarly, we have second document, we can do the same thing like this one. Then since this will be like two distributions, right, and then we can compute the KL divergence. And if this is close to each other, we say like these two documents are close to each other. And I just want to mention one thing as a remark is like people use this also to kind of just try to compare like one document with all possible documents, the distribution of all the documents in the internet, let's say. So then like for example, like I can have like a distribution one is like just a document, like I have again one document. Then I can see like how this document is like compared with like kind of in general some the distribution of all the words of across all the documents. So then in the sense I may have like a QW or like I use X, maybe I use DW as word, right? DW is like the distribution for this document. I have QW, I have distribution of another document. Then I can compute the KL divergence as a D. Here I use D1 here. Let's say this distribution is PW1. Let's say PW D other. Okay, sometimes I use D for KL divergence because, by the way, that's another because it's that's sometimes people use D also, like sometimes use KL, sometimes use D, but it's referring to the same thing. But let me stick with the KL here. So let's say I have like compute the KL divergence between P and Q. Then of course you remember the KL divergence is just like P W log PW over QW W. Then again I can write it as a sum WP W. By the way, I guess I need to check the that's okay. I don't know, it doesn't know how to automatic. I need to wait probably. This is pretty bad. Okay, come back. Okay, so I guess Beyond is also here. So now again come back to here. Is like we okay. Then for this KL divergence I can expand again. You saw this before. Like I can expand into some like this way. Like maybe PW log 1 over QW, something like that. My handwriting is ugly, but anyway, this is W here, and this is just the minus the entropy of P, right? And like often actually in this here, like let's say I don't care about the entropy here. I just want to see like how differ P with Q. So P is what I inquire, right? Something that like I don't count this HP here. Then again, like it go back, it boils down to again just looking into this term here. And by the way, this term, if you remember, like near the end, we mentioned that this is actually the cost entropy. But yeah, I don't have a special notation about that. It's just cost entropy between P and Q. And also like I want to mention one thing is like if you look at this, is basically counting for all W, like what's this term, right? Like for example, if I again like Q is basically distribution across all the documents, and W is for each of the word, right? If you look at this this quantity here, basically the word with this larger this expression is larger, then it will have a larger contribution to how you look at the importance of, or like how you look at that document is relating to all document, right? So in the sense that the larger this value for a particular W, that W will be more important, right? I'm not sure there's a name for this value here. Is looked at known as a TF-IDF. It's like actually term frequency and inverse document frequency. So if you work on NLP, like natural language processing, you may come across this term, this terminology here. But it's nice to know like where these things come from. It's basically just, it's actually just this one. It's basically the cost entropy, but not exactly the cost entropy, but it's for each of the expression that you're going to sum up into a cost entropy. And of course, this is basically is you can think of a function of W for a particular word. And why it's called TF-IDF? Because we look at like PW and QW. This I can also write it as a PW is, if you think of what is PW, PW is a given number of words in document D1 over total number of words in D1, and this will be the term frequency, like or you call it frequency, but it's like term probability, I would say. And then like the inverse document frequency here will be anyway. So this one over QW, I can write it as like the total number of documents over the number of documents with W. Or I should say this shouldn't be exactly equal to this, but it's like approximate. You can count like, if I think of like what's the probability having that particular word, you can estimate as like over all the possible documents in the world, how many documents have that word, over like the total number of documents, across everything you have. So then I'm thinking, I'm not sure I swapped that. This sounds like this is more like it's more like term frequency, this inverse document frequency. Yeah, but it doesn't matter. Like I don't. So anyway, like yes.
That yes. Will be 2 for the QW.
Yeah.
Or not?
Here?
Yeah.
Oh, okay. Here, okay, for this particular part here, like I'm not comparing document 1 with document 2, but let's say I have a document, I want to say like how this document, the distribution of the word in the document compare with like all possible words, like let's say in English, right? So to estimate the frequency of words in English, what you can do is like you just look at like for a particular word and see like for example like Oklahoma, like Oklahoma, how many times it occurred, like all the documents that you have, like maybe in a very large database with maybe like 1 million documents, and then like over like how many documents you have, then you estimate like the term frequency. I would say like the how the word is like kind of like appear frequently across the. Yeah, actually, yeah, I think this make more sense called term frequency, and this is an inverse document frequency. But anyway, so but if you look at that, it's nothing, but it's just cost entropy basically. So yeah, or to be more precise, like it's this term is really what contribute to the cost entropy. When you sum up this term, yes. So, you any questions from Norman? Yes. Oh, okay. I guess let me try to read this again. Yes. Yeah, you have some questions? No? So let me continue then. So yeah, that's I just want to bring out like kind of a remark, because it's interesting like how this is relating to like for example stuff you see like in NLP, like if you look at that from this perspective, then it's nothing special. So I guess I'll just mute BR for the moment. So okay, now let me start with some new things here. Let me just open a new page. So okay, we'll talk. So we mentioned the Kell divergence and kind of entropy, joint entropy. So now we'll talk about mutual information. Actually, interestingly, if you look at some very old textbook, sometimes they start with like all the definition for mutual information and expand out. You can say mutual information in some sense is more fundamental, because as we see, like for both continuous and discrete case, the definition of mutual information basically is the same. In the sense that like I'm not sure I should say that, but okay, now let me elaborate more later on. But let me start with like the definition itself. So basically, what mutual information is just like if you look at two random variable x and y, x and y, and the definition of mutual information is just like it's defined as hx minus hx given y. And we can also define some conditional mutual information. So for example, like the mutual information between x and y given z will be like hx given z minus hs given yz. So to jump ahead, like basically I will show later on, but this expression is actually symmetric. So when we say mutual information between x and y is actually the same as from y and x. So therefore, like it's actually this one, you can easily show that this is also equal to hy minus hy given x. Yeah, because actually you can very easily to see that, because if you move this to this side here, I mean hy given x move to this side and hx given y to this side, then hx plus hy given x is just hxy, right? Okay, this is not a good proof, but you see, like okay, so therefore, like basically you have like hx how do I write it? Let's see. Yeah.
There is not x and y, but x, y. Yes, that's correct. In here, there is not x and y.
It's x and what's that called? It's like semicolon y.
Semicolon y.
Yeah.
So that's different with x and y.
Yeah, actually it should be think of like the between x and y. So yeah.
There's another definition.
Yeah, that's defining this way. And when you define this way, actually this, of course, like if I write like this, it doesn't necessarily that ixy will be equal to iyxy. I mean, it's all obvious this will be equal to that, right? Yeah, but as you can see, let me just remove this first, maybe. As you can see, I can have like, let's say h, see, hx given y. Okay, this is like hx. Let's see, I can write hx given y as hxy minus hy, right? Yes. So then it readily you can see it's symmetric. Then you have hx plus hy minus hxy. And then of course I can do the same thing like back, and then this is equal to hy minus hxy minus hx, and this is just hy given x. So therefore like this, or from the definition, this is iyx. So therefore ixy is just equal to iyx. So this one is symmetric. And you can do the very similar kind of proof for ixy given c also. This will be just equal to iyx given c. And so, or like this will be equal to h. Let's try. I mean, let's go through this exercise anyway. So this is equal to hx given z, and this term I may write it as, let's see, minus h xy given z minus hy given z, right? Let's see. Yeah, I think it's right. So hy given z plus hx given yc, so it should be hxy given z. So given z, you know y, and then you try to look at, okay, given y, z again, and the information of x, and these two add together should be the information of xy given z, right? So then this again, this will be like rearranging the term like hx given z plus hy given z minus hy given z. And so therefore again like this is hy given z minus xy given z minus x given z. So this is like y given x. wait, is that right? Yes. Yeah.
Well, it's not it's not similar with the above.
It's similar. This one is then this term is like iyx given z, right? That's the definition basically.
Oh, yeah. That's
Yeah.
new.
See, yeah, yes. So yeah, I think this definition is symmetric, and also like actually, if you look at IXY, if I write again, yeah, okay, HX minus G is given Y, and this I can write it as a expectation minus log, let's say PX minus expectation log PX given Y. So that's remember that's the definition for entropy as well, right? And I can write it in a more, or like I can write it as probability. So Px log Px 6 there's a minus here. So Px y log P is given Y. So write that. And so I can, okay, let's see. You see like this thing here, the first time here, this does not depend on Y. And Px I can write it as a Px Y sum over Y, right? This is a Px, right? So basically, I can write this way. Do you agree with me? Yeah. So I just say this is equal to this guy, right? So this is equal to this guy. So then this is also somewhere xy, and cpxy is the same here, right? So I can group the terms together. So it's xy pxy log px given y over px, right? And then like pxy, I can multiply py on both numerator and denominator. So I will have like, so let's say multiply py on both numerator and denominator. What? Say that again?
Where is that come from? This one, this guy, and this guy.
Here. Oh, no, from here.
Oh, yeah.
Yes.
Yeah.
Yes, and then this is I go to this step here. Yes, and I'm saying I multiply py on both numerator and denominator. I have like xy pxy log p. So py multiplied by px given y is simply pxy, right? And then below is like px py. So actually from before, again, you see like this expression is supposed to be symmetric. That's what we expected. Like, but also one thing you can observe from here is like this is actually the KL divergence between like pxy and px py, right?
Yeah.
And that's really nice because we already know the KL divergence has to be bigger than equal to 0. So this kind of show that like IXY is bigger than equal to 0. And of course
that if independent, that will be same with 0.
Yes, exactly. Also like if x and y is independent, then you have like px y is equal to px py. Then this will be equal to 0. And that actually saying that like this x will be independent of y if and only if like IXY is equal to 0, right? So only if like x and y are independent, then x, y, the mutual information between x and y will be equal to 0. So it's very intuitive. Like if there's no, they do not share any information with one another, then they should be independent. So this is a kind of like,
There is no correlation.
yeah, very yes. There's no correlation, and actually, independent is actually a stronger condition than correlation. So because when you have a when you say like two random variables are uncorrelated, you're basically saying that, right? Like x, the two random variables, when you kind of like zero means both random variables, the product of these two will be equal to 0. Then we say it's uncorrelated.
Yeah.
But actually, like this does not imply that ixy
Not 0.
equal to 0. This does not imply that x and y independent to one another. On the other hand, the other is okay. So when x and y are independent, you make sure that it's uncorrelated. So you have like uncorrelated, and this is independent. So independent, therefore, like, is a stronger condition.
So
and
independent is will be uncorrelated, but uncorrelated
Yeah.
Sometimes not independent.
Yes, and also another remark is like if you have like Gaussian if your random variables are joint Gaussian, then these two conditions will be equivalent. When the random variables are also joint Gaussian, then like when the two random variables are uncorrelated, they'll be independent as well. So yeah, we can actually show that, but like maybe we'll do it some later time. So okay, what else I want to say? Oh, okay. And if you look at this here, if my random variable are continuous, then I probably didn't define the mutual information for continuous random variable yet. But as you can expect, that like if your random variable are continuous, the mutual information, it will be simply from the original entropy, and we replace all of this to like differential entropy, right? So then if like this, let's say if x and y, maybe I use another color. If x and y are actually continuous, then we'll talk about like some small h minus small h x given y. That would be like the mutual information between each other. Then I can still do this. Everything is basically the same way. Just the sum will be replaced by integral, right? This will become integral here. So I have integral like dx and this dxy here. So I can do the same thing. Like I can originally is only sum over x here. I'm integrating over x. I can integrating both x and y, and then this become like pxy here, and this, let's see, yeah, I should move here. So and I have like dx dy here, and then like basically this will change to something like that, right? And then basically everything is the same. I will have like this is equal to that. So I mean the mutual information for continuous random variable eventually be just equal to integrating over this. And again, like this is just the Carroll divergence, right? And so therefore again, like we will have exactly the same conclusion that like if your random variable, two random variables are independent, then the mutual information will be equal to 0. Otherwise, it will be bigger than equal to 0. And that's why I say like it's a bit more fundamental than entropy. If you remember, for continuous random variable, the differential entropy does not necessarily be positive. But here, the mutual information is always positive, regardless whether like you are looking at like discrete or continuous random variables.
Always positive.
Yeah, always positive. So that's why I said like some very old textbook actually like to use mutual information as starting point. They think it's a more fundamental, but I guess intuitively I think it's may not be. I don't know. At least I think the elaboration is a little bit more. The exposition is actually is to me is a little bit harder to start from mutual information.
Entropy will not have negative. Will not find negative.
No, actually we have. If you remember, like if I have continuous random variable, we can have like negative differential entropy.
Yeah.
The differential entropy can be negative.
Can be
But here, like that means that if you are looking at continuous random variable, the expression to measure the amount of information can be negative. But for mutual information, no matter whether you're looking into like discrete or continuous random variables, they will all be positive.
So what's the meaning of negative entropy in the continuous polynomial?
Actually, not very meaningful, because if you remember, like for continuous random variable, let's say, how you link with like continuous random variable to a discrete random variable, what you can do is say you quantize that way. I may have like a continuous random variable that maybe Gaussian or whatever, and then I can quantize that. After quantizing that, like that is a discrete. Then I can compute the original entropy.
Yeah, that's right.
And the connection, if you remember, is simply something like that, right? Let's see. I think it's minus log delta or something like that. Yeah. So therefore, like, yeah, it's hard to say like what's the physical meaning for that. Like, yeah. So but if you look at like continuous mutual information, what's going on is like you can also like, let's say if I look at hx given y, also I have x. Now I also have some other random variable. Maybe I start with is continuous, like x and y continuous, or maybe x is continuous. Then again I can discretize that way. If I discretize that, again I will have some h. I have some x delta. I can also discuss. Talk about like x delta given y, right? Something like that. And this will be, in the same manner, will be kind of like similar to that. Oh, here I just hand waving. Like maybe I will go to more. But yeah, if you want, okay, maybe I don't need to hand wave. But you remember this? We showed that last time, right?
Yeah,
or like several times ago.
That's right.
This is just saying, okay, because if you think of like what is conditional entropy, is just basically something like p x y log p is given y, or I can write it as px py, oh sorry, y p y given, oh wait a sec, wait, let's see, p x p is given y. I probably should, wait, I need to go back. This is y sum over x, p x given y log p x given y. So of course I have some negative sign everywhere. Yeah, but this one you look at is just entropy, right? It's just entropy, but it's like for different y you have a different entropy, right? And you kind of taking average, right? Weighted sum for all this entropy, right? Depends on the distribution of y. So then of course this will be just, I would have this this can be shown very easily, because I basically have like hx delta given small y equal to h, or like I shouldn't say equal, but approximate hx given small y minus log delta, right? This is just like the same thing for this one, right?
Yeah,
There's nothing.
right.
And then if I take average over all the y here, I will get this way.
Yeah.
I mean, if I average over like, so therefore like, yeah, I have both of these. Then like, if you think of like what is mutual information of IXY, will be just H, or like HX IX delta Y will be H X delta minus H X delta given Y, right? So it will be like H X minus H X given Y, right? Basically the log delta will be cancelled.
Log delta will be cancelled.
Yeah, I mean like this is like minus log delta, and this is minus log delta,
Oh yeah, that's right.
right? And then log delta will be cancelled.
Mhm.
So then you can see that like what's nice is like when you talk about mutual information, because this log delta is cancelled, no matter you're talking about the continuous random variable or the discrete, okay, continuous random variable or the discrete random variable, it is it doesn't, how should I put it? Maybe think of that this way. If I vary delta, like delta continue to decrease, right? Delta continue to decrease. In this case, like for the original entropy, like you have the quantized version will be getting will keep become bigger and bigger, right?
Bigger when the delta is decreased.
Yes, when delta decrease, this will become bigger and bigger, because minus log delta will become bigger and bigger.
Oh yeah, that's right.
But here, you change delta whatever you want.
There's no change. Anything.
There's no change. Yes, because the log delta just got cancelled.
They cancel to
Yeah,
each other. Oh. I see.
and
then in the entropy, that will be negative because the log delta will be.
yeah, because it can be
Yeah.
positive,
Yeah.
negative. Yes, so
Yeah.
therefore you cannot control the sign.
Yeah, that's right.
Yeah. So yeah, we okay. We also, yeah, that's nice. This is very good. You bring out a nice question here. So let me also look at the conditional and mutual information. So Ix y given c there. What time is it? Yeah, Ix y given c. And basically I can more or less do the same thing. I can write this as a sum over x, y. Wait. This is a, maybe I will just write it out first. Hx given z minus x given y z. And this, the first term is basically px z log p x given z. So this is a sum over x and z, and this is a, there's a minus sign here, there's a plus sign here, p x y z x y z log p x given y z, right? Now I can do more or less the same. Okay, first of all, let me pull all the x out. Others, no, x and z out. Yeah. I can write this as a p z given p x given z multiplied by p z. So, and I can write this as a p x y given z p z. So then that will become pz. I pull out first, and x p x given z, yes, log px given z. So this again, it's just the entropy, right? For for x, basically entropy for x become parameterized by z here, and then this is a z again, p z sum over xy, p xy given z log x given y z. So, and then I can group this z together, so sum over z, p z, this x. So now I can, like previously, I can add y here. Also sum over y. So what I need to do is if I, let's say, I insert y here, and sum over y, then I will get back px given z, right? Or let me write it this way. This is actually just equal to y px y given z, right? Yeah. So therefore I can.
Inside you not
Yeah.
you input also pxy. Over here, you not input pxy also.
Oh no, this one I don't care actually. Let's see. No, this one no. I shouldn't. I cannot. So okay. I mean this one is equal to sum here, right? So of course I can substitute also this guy by this term here, but I don't want to do it. I will have a log something. This is very ugly. This is not something I want. And the rest of the term here is a xy. So this pc here comes to here, right? So I have xy p xy given z log p x given y z. Yes, I missed a p here. Okay. So so now you can see these two is the same, right? Again, I can group together. It's a z p z sum over xy p x y given z log wait a sec. I probably want to remove this minus sign here, then this will become px given y z over px given z. Let's see. Wait, I think I have something wrong somewhere. Oh no, it's right. So now now then again, similar to what we did before, if I multiply py given z to both like numerator of denominator here, then below will become like log px given z py given z, right? And above is basically what? It's like p x y given c. It's hard to write z. And of course this is equal to this, the same thing, right? P x y given z sum of x y. So very nice again, like this is actually just the Taylor divergence between like p x y given z and like p x given z p y given z, right? But you have something else here at the beginning, p z. Yeah, something like. So, and of course, Taylor divergence is positive always. And so therefore, like again, like this term will be bigger than or equal to 0. So of course, PC is positive. And for this to be 0, you need to have like all the Taylor divergence for each of these is equal to 0. So for each of the z, I will have like pxy given z is equal to px. Basically, I will have like pxy given z is equal to px given z times py given z for all z, actually for all x, y, z. And this is actually just saying that x and y are conditionally independent given z. Yes. So yeah, I think we mentioned that in the first class.
Conditionally independent.
Yeah.
But why?
Oh, you mean this one?
No, that's yeah. This requirement to this one. So why? So you can.
I guess it's hard to say why, because like this is similar to this, like x independent of what to y will be like pxy is equal to px times py.
Okay.
This is actually just an analogy of this one, basically, essentially. So
when given z.
Yeah, given z, yes.
Oh, I see. Because there is z in there.
Yes.
This one is z. Also
Yes,
given
yes,
z,
yeah.
z. Oh, yeah, okay. Understand.
So and
so that is mean that only separate of x and y will be independent only when given z.
yes.
Not all of x and y is independent. Not all. Only in the z portion.
Yes, but you need to be careful. Like, you sound like that. Like one condition is stronger than the other, but it's not. I mean, like, you can find cases like x and y independent, but x and y are not conditionally independent given z. But you can also find, example the other way around. Like x and y are conditionally independent given z, but not independent to each other.
Not independent each other.
Yeah.
But x and y, if x and y independent, so that will be x and y independent given z.
No.
No.
No. This is so. No. This is not. Actually, I guess we mentioned one of this example at the beginning. I forgot which one to which one, but let's say if I have like. You're thinking like x and y independent, then doesn't mean that x and y will be conditionally independent given z, right? Something like that. But no, for example, like
using short.
Yes, you remember that you have homework problem or something like I forgot that you have x and y, right? Independent. Just like some folding a dice or like flipping a coins, like these are independent coins. But you can have like c is just equal to kind of like the sum of the outcomes, let's say, right? Then in this case, for example, flipping a coin, you know z, x and y is totally depend on each other, right?
Yeah.
So you can also think of other example like x and y are conditionally independent given z, but x and y are not independent. For example, like just another very simple example. Let's say I have a let's say z is the current temperature, and x and y are basically like kind of measurement from two kind of thermometer. So this is from thermometer 1, and this is a measurement from thermometer 2. So given z, x, y will be independent with each other. So this is kind of like that kind of Markov chain, that this z itself is the source of two different this is like two other variables, a common source for two other variables, and these two common sources only depends on this. These two other variables only depends on this common source here. So knowing this common source, then x and y will be independent of one another. Make it very concrete. For example, like this both of these x and y will be just equal to this at some Gaussian noise. So with some variance, some independent Gaussian noise, this is just a z plus, and this is a c plus Gaussian noise, I say, right?
Yeah.
Then in that case, it's very obvious. If given z, this is just like two noises here, right? They should be independent of one another.
Yeah.
But if you are not given z, they should be dependent on each other, right? Because they are all both very related to this z here. So yeah. So therefore, be very careful, when you talk about independence and conditionally independence. I guess that's an intention, as you just mentioned. At the beginning, where lots of students are looking into this tends to think, okay, if I have something is independent, then it would be conditionally independent as well. But no, yeah, you just have cases that you can have one way and the other, and you can have the other but not the other way, or back and forth and so on. I guess it's clear, probably. So, I think I'm not charging somehow. This is not charging. Why this is not charging?
Not charging?
Wait a sec, maybe. So this one is I think I have.
That's on.
Set has the set has let me try. Yeah, that was working last time. Let's see. Okay, now it's charging now. So
that is depend.
yes. So yeah, I guess that's what I want to say about age. Okay, now next thing, let's look into some chain rules for visual information. We have chain rules for joint entropy. If you remember, for example, if I hx1, x2, x3 given y, then it will be something hx1 given y plus hx2 given x1 y plus x3 given x1 x2 y, right? Stuff like that, right?
Yeah.
So we can have set. I have a typo here, actually. I can have, let's say, visual information x1, x2, xn, let's say y. Then this one will be hx1 xn minus hx1 xn given y, right? Stuff like that. And then here I have chain rule that I can write as hx1 plus hx2 given x1 and so on to hx and given x1 to n minus 1. So sometimes we can write like this, it's more convenient. So this just means that x1 up to xn minus 1, x1 is 2 and so on. And minus this will be hx1 given y, right? Plus x2 given x1y blah 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 up to hxn given x1 to n minus 1 y. So now I can subtract each of these terms, like kind of corresponding term like this to the first term of this inside the bracket, and this subtract this guy. Each of them will be an mutual information, right? So hx1 minus hx1 given y will be just ix1 y, and hx2 given x1 minus hx2 given x1 y is just x2 what?
X1.
No.
That's x1. Y.
Yes, y given x1 actually.
Yeah.
Yes, and similarly, so it's like the final term will be like ixn, yeah, ixn and y given x1 and minus 1, something like that. So we have a chain rule like this. So something like I can write it as a summation. So it's like sum over ix I y given x1 I minus 1, something like that. And of course I can also have put a condition, look at the conditional mutual information. For example, like I can consider like ix1 to n y given z here. Then I can do more or less the same thing. That would be like hx1 to n given z minus hx1 to n given y z, and then that would be hx1 hx oops given z plus hx2 given x1 z blah 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 hxn given x1 n minus 1 z minus x1 given yz plus hx2 given x1 yz blah 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 hxn given x1 n minus 1 yz, something like that. Yeah. And so then the first term is a x1 yz plus x2 y given x1 z, right, and so on. Xn y given x1 n minus 1 z. Yeah, so this y as a summation will be ix I y given z c and x1 I minus 1. Yeah.
Oh yeah, see there.
It's
Actually same with the above. But
yeah, but to see here, so your condition we see, you will see like everywhere. And if you change everything to continuous random variable, then it will be exactly the same way. So I can have like this all small h here. So this chain will still hold. So basically, like this chain will hold like no matter it's like continuous or like discrete random variable. So basically, like more or less, like this is also true, like for everything else we mentioned, like when ixy is equal to 0, that imply if and only if x and y independent, and ixy given z equal to 0 if and only if like xy are independent given z. So this does, I mean, all these holds regardless, like whether your x, y, and z are discrete or continuous. They just hold like for all combinations. So yes. And by the way, like because we just showed that like I, x, y kind of like mutual information has to be bigger than or equal to 0, right? And we know that from definition, this is just hx minus hx given y, right? So you see that like always, like when you're given something like this was bigger than or equal to 0, that means that hx is bigger than hx given y. And we also have something like if I have ix y given z bigger than or equal to 0, this is equal hx given z minus hx given y z. So again, this is bigger than or equal to 0. That means that hx given z is bigger than or equal to hx given y z. So this is this kind of condition. I mean, inequality is known as like is sometimes referred to as like conditioning. Reduces entropy. Right. So if you have some random variables and you try to estimate its entropy. Now, if you know some extra information, for example, you know y now, then the entropy, the random variable you are looking at, again, of course, the uncertainty will decrease, right? Given the new information. So therefore, this is actually very natural. So whenever you are conditioning something more, that basically you know something more, the mutual information will just decrease. No, mutual. The entropy, yeah, the entropy will always decrease. And this again, this will be the this will hold no matter you are considering like discrete or like continuous random variables.
If we know something, that will be decrease the entropy.
Decrease, right? Yes.
Because
so,
we know something.
Yeah, you already know something. Now you ask a question. Like for example, x is whether tomorrow is going to rain. Like you have like a yes or no, right? So y can be like, for example, whether the ground is wet, or like whether today it rains, or like stuff like that. Like each piece of new information will make decrease the entropy. So making like your question, the potential answer is more and more certain. Like the uncertainty will just decrease. Yes, and let's talk about another inequality. It's known as the data processing inequality. So basically, you first of all, like for this data processing inequality, we need an assumption for the inequality. We assume that like x, y, let's put xc is conditional independence given y. So, or I can write it as a Markov chain that x, y, z. So again, these are basically equivalent. So so when you say like xmc conditionally independent given y, you can write it this way, because actually this is very natural to write it this way, because this is like a chain of information. Now if you remove some of this in the middle, you just break the chain and then these two become independent. So it's like quite intuitive way to memorize this. So if you have this condition that x and c are conditionally independent given y, then we will have like I, x, y. The mutual information is between x and y will be bigger than equal to I, x and z. Yes, the mutual information between these two will be bigger than equal to the mutual information between these two. So let's just look at a simple proof for that. So I, x, y, I can write it as like I, x, y, z. Oh, actually we never look into like we didn't, right? But this is like the same kind of definition, right? Remember, like if I mean, I think we didn't look at cases like, for example, I, x, like x with like multiple random variables. Yeah.
Could I?
Yes. Yes.
This one, there is some formal mathematical to prove it.
Yeah.
Yeah, because this I don't get the yeah.
Yes, we are proving this. We are trying to prove that this is the proof.
Oh, that's the proof.
Now we talk about the proof. So let's see. What I'm saying is, for we didn't define this. Did we define something like that? But it doesn't matter. Like if we have something like this, it's just that we can consider this as like h, y, z minus h, y, z given x, y. Yeah, and this is therefore is a h, y. Wait, actually we did, right? Oh, okay, we did. Okay, I'm kind of silly. We did that because it's symmetric. Okay, this is just chain rule. So let me. So this is just equal to, let's say, I get more familiar looking into the other way. I, y, c given x, so it's symmetric. It's just like that. Then I can use the chain rule. It's like I, y, I, x.
Y, z given x.
Let's see.
Y, z given x. That's not same.
Oh, okay. I'm sorry. This is of course not the same. I should say, like, let me consider this first. This is equal to I, y, x, y, c, x. So I can write as a I, x, y, or like I, y, x. Let's say I, y, x. Let me write I, y, x.
I, y,
x plus I, c, x given y, right?
Given y.
Yeah, that's the chain rule that we just show like earlier on. This just using the chain rule here.
Oh, there.
Yeah, here.
X. Oh, okay.
Yeah, just using this. So and then so because this is equal to that, then I can, so therefore like I, x, y is actually equal to I x, y is actually equal to I, x, y, z. This basically this term minus I, x, c given y.
Where is the R, X, Y in here?
I, x, y here.
This one? Here?
Here, yeah.
Oh.
Yeah, it's the same thing, yeah.
Oh, okay.
I just flip the y's to I, x, y.
Oh, okay.
Yeah.
That's right.
Yes. So then now then of course this is equal to 0, right? Because we have the assumption here. We have that is conditional independence given y, so I, x, c given y should be equal to 0.
Oh,
yeah, that we just have that. So therefore, like this is equal to this term only, I, x, y, c. But what is I, x, y, c? I can expand it in other way. it will be ix z plus I x y given 0, right?
Yeah, that's right.
But of course we know that like mutual information is always positive, right?
Yeah.
So therefore like this will be bigger than equal to I x y given z. Oh, sorry. This is not I care. This will be bigger than equal to I x z, right? So this is bigger than equal to 0.
Oh, yeah. That's bigger than that.
Yeah, so that's already proved. So I x y therefore is bigger than equal to I x z.
Because this is bigger than this, because this is bigger than this.
No, this one is positive, right?
Yeah, that's positive.
So something plus positive is bigger than equal to this something, right? I mean, this is I just copy from here.
Something with positive will be bigger than that's one. That's mean that the this one more bigger than this one. This one more bigger than this one.
Oh wait, my handwriting is that like this two is the same. This is two. This is both of them are IXC here. It's just here IXC plus something here, and because this something is positive, therefore it's bigger than equal to IXC, right?
Oh,
so it's like yeah.
Oh, okay.
So and
that is why. That is why.
Right.
In here there is why.
Yes, but it doesn't matter, like because remember the mutual information we showed earlier on, like for both like conditional mutual information and also mutual information, all of them is larger than equal to 0, right?
Yeah.
All of them are positive. Here I don't care like what this is, but I know this is has to be positive, right?
Yeah, that's
because this has to be positive, then therefore like this IXC plus some positive values has to be bigger than the IXC itself, right?
Oh.
So therefore like
yeah, and then this one, this is
yeah, this is equal to that IXY.
IXY. Oh,
Yes.
okay. Oh,
So therefore IXY is bigger than IXC.
Oh, okay.
So yes, and one way to think of that is why people call data processing inequalities. You can think of like the Markov chain is coming from like you have some data coming in, some original data that some kind of information. Then let's say it's being processed, right? So maybe there's some process like after the process you get Y, and then you process again you get Z here.
Yeah.
Now let's say you from this Y and Z you're trying to recover to the original X here. And the data processing inequality is that like if you're trying to recover the original X from the processed information here, the more processing you have in the later on, it becomes more difficult to get back the original. Because like you are losing the dependency here. Like if you look at the dependency between X and Y and the dependency between X and Z, the dependency between X and Z is smaller than dependency between X and Y. So therefore like this actually is saying something like actually this is kind of have some interesting practical argument. For example, let's say if I trying to do let me give one example, very concrete example. Let's say I have a computer vision, kind of that kind of application that I'm trying to have a sign here. Have a sign.
What is TV?
Computer vision.
Computer vision.
Computer vision application here. So let's say I have a sign. Let's say I'm doing a kind of like sign recognition program software that I have some sign that is kind of like have the camera, have the computer trying to read some traffic sign there. Now, so I can just derive a program, a software, an algorithm, directly process this to extract the sign, to read out this sign here. Or I can have this image coming in, first go through some denoising step and some kind of like super resolution step, maybe let's say super resolution to make it bigger, let's say, and then like afterward like I try to recognize the sign. So intuitively you may argue that okay, of course if I do some denoising and super resolution and so on, I probably will get a better result. But from the data processing inequality is saying that like this will not help you theoretical wise. It will simplify the step, but if you have some optimal algorithm somehow to process your image, like from the original image, I'm trying to extract the sign directly, you actually, the best algorithm from that one will always better than like trying to process after this denoising and super resolution step. So, but of course in practice, like it's hard to like devise a kind of design an algorithm to kind of extract like optimal kind of like recognition from the image directly. So, but if you're able to do it, it's actually will be better than like you go through all this denoising supervision. And actually this also like have another argument is like why deep learning that kind of like probably makes sense is like you don't need this intermediate step. Like if you think of like deep learning and so on, like typically they don't have too much like pre-processing step. So if you can do this step like optimally, this pre-processing step is unnecessary, actually can be even be harmful.
Because that give some entropy, denoising.
Actually this step like is like this step here. You will always lose the dependency to the original.
Always lose dependency.
Yeah.
So more independent in the next step.
Yeah, but when you become more independent, it means that like you get less and less information regarding the original, and so therefore like you can
lose some information because denoising, not gain up the information, not more clear the information. If we use denoising.
It doesn't matter whether you use denoising, super resolution, or deburring. Like all this will be like a step that you kind of like, because this step will all obey this like Markov chain here. So if you from here you have like output x, and let's say from after this step you got output y here,
so how to explain that we lose some information by using that equation of all?
Oh, let me actually I shouldn't write this as x here. Maybe let me think of like x is here. So x is like some underlying truth that the sign is that the sign is showing the sign is universal or comma or something like that. Some fundamental fact. And from that, like you can think of like there's some imaging, like generating the image, right? Somehow that will eventually get a y here. And then this y go through the process, you get a z here. And the argument here is that like you will have a Markov chain here. No matter what kind of process you have, you still have the Markov chain is still there. Basically, like given y, x and z will be conditionally independent. And that alone is sufficient to show that like you will have the mutual information between x and y will be bigger than x and z. So therefore, if you're trying to extract the fundamental truth of what the sign is written there, coming from here is more difficult than coming from here. So
even there is no denoising.
Yeah, even though you're trying to denoising and so on, but of course it depends on how you're going to do it, right? In practice, you don't know how to do it, then it's easier to do. But what I'm saying, like for example, if you use deep learning and so on, that's people do the end to end, and somehow if you have enough data to do the training and so on, then it really shows that like you actually do not need those intermediate steps there, right? People are actually following more and more intermediate step away. They just do a very simple like kind of normalize the mean and so on. So
or that, and then that's the equation proof that process that mutual information from x and y is more bigger than x, y, z.
X, y from bigger than x and z. Yes.
Yeah, x and z. Yeah.
Yes.
So z, that is intermediate in between.
C is here. C is here. C is after the.
After that.
Yeah. So okay, maybe we'll just take a break for 15 minutes again. I come back like around like I don't know, maybe 35 or 36. I don't know. Yeah. So.